Alright, very good morning to all of us. Today we'll start on a new chapter, Unit 21, Electromagnetism. We'll be building on two previous parts. One is on magnetism and the other one is on electricity. So these two can come together itself and they are able to change from one form to another very easily. So let's take a look here. Okay, so the first part here, what we want to do is to find out on how an electrical wire itself is able to produce a magnetic field. So in the previous chapter, we know that when we have electromagnet, we can make an electromagnet by passing a current through an iron nail. So what we have here is the iron nail. This is iron. And in this here, is have a solenoid. That means a wire being coiled around the iron itself. By running a current through it itself, this can become an electromagnet. So we have already showed the first demonstration of when a current flows through, it can have magnetic properties to become an electromagnet. Now let's study this more in detail. There's this scientist Hans Christian Ørsted discovered in 1819 that an electrical current produces a magnetic field. So what he did was he closed the circuit here. So he has a circuit here that he closed. Current is able to flow through. And when current flow through itself, he realized that he has two compass. One compass is placed on top of the wire, and another one is placed under the wire or below the wire. Okay, let's change it to below. So when he placed these two compasses were supposed to point north because based on the geographical nature, all compasses will point north. It's supposed to point north, but no, when he closed the switch itself, he realized that the compass current flowing through XY, neither of compass A, which is the one above, pointed to the east. He noticed that the one in compass B, which was placed below the wire, pointed to the west. So he realized that there is a magnetic field being produced when current flows through a wire. So what is the magnetic field pattern like? The magnetic field pattern is as such. Imagine this is a wire and there's a current going upwards. So the sharp end is where the current is flowing. I take my right hand grip rule to identify where is the direction of the magnetic field lines. My thumb follows the current and I grip it. So if the current goes up, my thumb also goes up to point the direction of the current, and my fingers will show the direction of the magnetic field. So in this case itself, it goes in a clockwise, anti-clockwise direction if I look from the top. So your right hand grip rule can tells you the direction of the magnetic field. So let's explore it further. But before we go any further, let us talk about the two main points, definition that we'll use throughout this page itself. So when we have an arrow, so this is an arrow, we have an arrowhead here. So the arrowhead is sharp. So if we look from the top here, we realize that what we see, if you look from the top here, what we see is a sharp area. It means that the arrow is coming towards you. So if we use a dot in a circle, it means that the current is coming towards you. Okay, towards. But if we look from the back, if we place our eyeball here, we look at the back, we realize that there's a cross section. It shows like the arrow is moving away, so the current is moving away in this case. So just take note, we use a cross to denote as a current moving away and a sharp dot, to show that the current is coming towards you. So let's look in this diagram here itself. When the current is coming towards us, we use our thumb will point towards us itself because that's the direction of the current. The fingers give us the magnetic field. Okay, so in this case it's anti-clockwise. Let's look at in this diagram here itself. Now there's an X means that it's going away from us, means your thumb must be going away from us and it's moving in a clockwise direction. So that's the magnetic field. Okay. So notice that in the middle here, you can see that the lines are closer as compared to outside. If we draw two same boxes, sorry, let me draw the same box. Okay, you notice that the number of field lines is lesser outside as compared to nearer towards the wire. So what it means, when you're nearer towards the wire, the magnetic field is stronger. When you are moving away from it, the magnetic field strength decreases. Okay, so we look at the density of field lines there. The more lines there is, the closer they are, the stronger the magnetic field strength. Okay, so there are two factors that affect the magnetic field strength. Number one is the distance from the wire. As I mentioned, the nearer you are to the wire, the stronger your magnetic field strength, and the size of the current. So the larger the size of the current, the stronger your magnetic field. Okay, so the direction of the magnetic field can also be reversed when the current changes direction. So if we were to switch, as shown in the diagram here, if we were to change the direction of the current, whether it's coming towards you or away from you, you can see that the magnetic field lines actually change direction also. So vice versa, if you can change the magnetic field lines, you change the current also. All right, so once we previously we talked about a straight line. Now let's bend, sorry, we talked about a straight wire. So now let's bend this straight wire into a coil, a flat coil here. So there's literally two wire, one coming out and one going in. Okay, so this is a flat coil. Using our right hand grip rule, our thumb to show the direction. This wire here gives us a anti-clockwise, and the other wire that goes down gives us a clockwise if we look from the top, and it gives us this field pattern here. So you can draw the field pattern of a flat coil as such. Okay, so what we want to take note here is that it has to be symmetrical. There's one field line that goes through the middle here that is unaffected because they both reinforce. As you can see, there's a lot of field lines in the middle here, means the magnetic field strength is much stronger. The other magnetic field will go around. So you draw circles to show the magnetic field lines, and same for the other side. Okay, so you can trace out the pattern itself. This will be the magnetic field lines for a flat coil. Now, instead of just one coil, so we started off with a wire, then we started with a coil. What happens if we keep turning it? What we get is a solenoid. So now let's look at the solenoid itself. In a solenoid, previously we used a right-hand grip rule. So I'd like to clarify that right-hand grip rule can be used for two stuff. Number one is to use to identify where is the north pole for a solenoid. And another one is to identify your magnetic field pattern, your magnetic field direction when you are using for a wire. Okay, so in this case, previously we have used the first part to identify north. So your fingers will follow the direction of the current, and your thumb will tell you the north pole. So down here is north and down here is south. So now itself, we would like to draw the magnetic field lines around this. So each of these wire, so you can see the current comes in here, goes here, comes out here. Okay, so you can see that each of these is like a single wire on its own. If you use your right hand grip rule to show the thumb direction, you grip each of these coil, it shows you the magnetic field pattern, and we can easily deduce it as north and here is as south, because if you use your right hand grip rule, you grip each of the coil here, the current going up, you grip each of the coil, it tells you that that's north and that's south, and this will give you a magnetic field pattern similar to a bar magnet. So how will it look like? It will look exactly like this. Move from north to south, and that the lines are symmetrical. Take note that the lines in the middle of the coil, they are uniform. The lines in the middle here, they are all uniform to show that the magnetic field is uniform and that they are equally, and that the field lines are equally spaced out. The strength is uniform, just to reinforce again. Away from it, it flows from north to south, so it closes the loop. So it feels like a bar magnet. Okay, there are three factors that affect the magnetic field strength of solenoid. Number one, the current. So if you run the current through a larger current, the magnetic field strength will be bigger. If you increase the number of coils here, so the number of coils increase, number of turns per unit length, that means each length itself there are more coils, number of turns, your magnetic field will be much stronger also. Last but not least, you want to concentrate all the magnetic field lines in the middle there. Bring more lines and concentrate it. One way to do it is to put a soft iron core, because the soft iron core is easily magnetized. You can draw all the magnetic field lines towards it and increase the magnetic field strength. So these are a few ways to actually increase the magnetic field lines. So we have talked about three types of situation where we can have a magnetic field. Number one is a wire. Number two is a flat coil, which is only one coil, and the third one is just a solenoid, which is similar to a bar magnet. All right, so this is part one. We'll come back to part two to talk about the uses of these electromagnets. All right, thank you.